Hello everyone. Welcome to this week's ASAP seminar. I'm Sony. I'm here to host for Xinyu to avoid him hosting himself. And today's talk is kind of a special one, not just because the topic is exciting, but also because the speaker is technically one of us. Yeah, we've definitely finally reached the point where our own speaker, on the own organizer decided to submit to his own seminar. And Xinyu is one of the co-organizer of this ASAP seminar, and he's a PhD student at CMU, working with Betty Chen, and he's working at the intersection of system and foundation model. Today, he will be presenting Multiverse, a new framework that rethinks how LLMs generate not just token by token, but in parallel by splitting and merging tasks in a map-reduced style generation. So let's give a warm welcome to Xinyu, and I'll hand it over to you. Please get started.
Yeah, can everyone see the screen? Yeah, yeah, yeah. Hello, everyone. Yeah, I'm the one of the co-organizer of this seminar. Yeah, because that we recently have a very interesting work that archive multiverse. So I just want to present here as of my. I think it's the first time that I present maybe in English. It's the first time. Yeah, just want to share in my own seminar this time. Yeah, its name is Multiverse. Your language model secretly decide how to parallelize and merge generation. This is a work done at CMU with collaboration with my advisor Beidi Chen and Professor Tianji Chen and our collaborator Yu Wei and Hong Yi. Yeah, and it's work from the Infinity AI Lab and CMU Catalyst. First, I'd want to show everyone a demo. I think that most of people in today should see the demo, but afraid if there's no people do not see it before. Yeah, let me show the power of multiverse. Yeah. Yeah, we can see that multiverse provide a new solution to the recent one recent things that people are really very care about is about how to generate in parallel. We know that many people recently they work on the diffusion models that to enable parallel generation, and we are also working on this direction. So the first question is that why parallel generation is so important, and so this is our motivation. Yeah, I'd like to refer to another work that's released by our group recently, yeah, but with a few modification. It's about we consider a case that if you want to use an regressive model to generate one token, what do you need? The first is that you will have in the both attention layer and in the MLP layer, you will have many linear layer, which means that just do the matrix manipulation, which means that you will have many computation on this. The computation is 2 times n times p because that they are just multiplication and p is the number of the parameter. And the second thing that you need to do is that you need to calculate about the self-attention because that currently that we only consider the generate one token, so we only have L in, L out is always one, and we omit it, so that we can see that these are all the computations that we need. And in addition to this, that we also need many memory access because that we need to load the memory from the GPU to the tensor core. Yeah, so that we will have two kind of the memory access. The first is the KV cache access, which means that we need to load the KV cache from our GPU to our core. That this will require these numbers of the GPU memory access. And here we are different from the case that we do not consider any prefix sharing because that we want to think about, for example, if we want to maybe parallel something that during the middle of generation, what happens? I think that we can. Oh, just. Yeah, yeah, it's okay to ask any questions. That if you have any question, just just write it in the chat and I will answer it. Yeah. Also, or you can just ask. Yeah. And oh, here I is just I think I can just explain here. Yeah, Here, n is the number of the bar size, yeah, and p is the number of the parameter. I is the arithmetic intensity. It will be a fixed number for each hardware. Just means that it's just a ratio between the maybe the model's ability of the calculation and the memory access. We just add this I to just make up just combine the calculation and the memory access to make that they can be compared. And R is the group size in the group query attention, because that in the group query attention that for each for each group that we can share the same KV, so we do not need to computation all of them, so that we need this group size. And D is a hidden dimension, just means that with this value you can calculate that how many that just a transformer model can calculate and can access the memory. Yeah, let me see. Yeah, so that in this case that we want to consider several cases. The first case is about in the small batch size scenario. For example, if the number of the batch size is 1 and let me check the max. Yeah, I think the max arithmetic intensity. Just we want to know that if the model just can make use of the hardware, it is just bottlenecked by the memory or by the computation. Yeah. So that we can go back that when we consider a small batch size, that if the number of the batch size is 1 and the input sequence length is about 4,000 and I is 500, this is a number that of the B200 GPU, and P is our 32 billion model, and R, the group says we set it to 4, and the hidden dimension is only 4K. That if we just compute these four numbers and add them together, we can find that in this short sequence case that the parameter access will occupy 90% of the computation or maybe the time, so that it is in a small batch inference settings that your model will always bottleneck by the I/O compute, I/O access that for an auto request model. So what if we want it to be compute bound, we need to increase the bar size, because we can see that the parameter access is something irrelevant to the bar size, but the linear modules computation is something relevant to it. So that if you compute it, you will find that you need a bar size of 700, more than 700, to make sure that your compute to be balanced with your memory access, so that we can think that for small batch inference settings that your model will be always bottlenecked by the memory access. And the second case is about we consider another case that which means that when you want to generate a very long context, what will happen? Just means that in this case we set the input sequence length to be 32K, and we will find that in this case that your computation will be your time will be bottlenecked by the KV access. So after our calculation that in this case the model will never become compute bound, because that the equation have no answer. So that you can think about if you want for current reasoning task, if you want to really do test time scaling, generate very long answers, your model will finally bottleneck by its memory. So that we find that autoregressive models should be I/O bottlenecked, so that we want to mitigate this I/O bottleneck by enable the parallel generation. So that you can see that we just draw a figure here, just means that currently that I think the current serving engine mainly consider short input with a large bar size, and in this case it becomes compute bound. But in the other three cases, the model is always I/O bound, so that we want to just input the number of the tokens input at each time step, so that the model can shift from the I/O bottleneck to a little more of the compute bound, so that even if I do much more compute at the same time, I do not increase the overall latency, because that I still use the same number of the I/O access. Yeah, this is, I think, the first motivation why we need parallel generation. And so that we can see that there is another motivation is about throughput is not everything. I think that I just reference a paper from the one paper of the I think the PD dispatch about a comparison of the throughput and the goodput. which means that you will have so many users, and I think that some of the users they care about the throughput, and some of the users they will have maybe some specific requirement for the latency, which means, for example, they have both the time to the first token and the time per output token that they have a own requirement. So that if you consider that you just think about the throughput and input a large context length, a large byte size, that for each single user, it has to wait a long time to get the output for a long generation. So that if there's, for example, a VIP user that he wants to a very fast generation, that autoregressive model cannot accelerate this process because that it is IO bottleneck. If you want to accelerate, you must do much more compute or just generate more than one tokens at each single time step. Let's see that. Oh, no more question. Yeah. So from the above analyze that we find that our goal is that the generated speed or latency is bottlenecked by the autoregressive generation. So that we want to enable some fine-grained parallel generation within one samples, just generate more than one tokens at the same single steps. But so that we mentioned that how they address these two challenges. The first thing is that because that most generation is IO bounded as we analyze, so that this will not increase inference time because that both the parameter and the KV cache can be shared within the single example. The second thing is about we need to care about latency or the good put, and parallel generation can reduce the sequential generation steps. And we mentioned many prereqs has exploring this direction, but why they do not solve this problem. The first that, as mentioned before, that we see that recently many people are doing diffusion models. But for diffusion models, the problem is that diffusion models just practically that they just initialize a very long context length and they just brute forcefully predict the output for the whole sequence at each time step, so that they are requiring many denoising steps, because that if you imagine that there are some tokens, they have some sequential logical dependency, you cannot generate both of them at the same time. So that diffusion models, they waste a lot of the time to do some wasted compute. And if we do not consider Gemini diffusion because they are super strong, that I think that for the open source works, we currently we do not see any of the diffusion models work for the real world reasoning tasks such as AME, something like this. They only at most they must work for some tasks like GNZK. So that we still do not know that how diffusion generally performs in the real world challenging task. And the second case, I think that many people try to modify the autoregressive generation process with some parallel scaling to enable this ability. For the most oldest one, we have best of n. Then we have something like MCTS or tree of thought. And recently, we see some more work on this direction. But a common problem is that they typically relies on the external tools to merge their results. For example, after you do best of n, for example, you have n results, you need an external verifier to decide that which one is the most important one. And it's hard for you to move if you are on, so that if you shift to some task without some ground truth verifier, that the model itself cannot try to just combine the information from different branch natively. So that we think that this ability will be bottlenecked by the verifier, and we do not want to rely on any external tools to do this parallelism. So this comes to our second goal, that we want both adaptive and internal parallel generation. Because that based on the previous limitations we discussed, we find that there are totally different on these two kinds of the methods, that the diffusion models and the other method. We find that diffusion models, they are always focused on the token level parallelism, which means that you can generate several token in the same time. So that we think that it's hard it's hard for it to maybe adaptively split between that which two token can be generated in parallel and which two cannot, because that this is so fine-grained. And if you do this thing, that you need some additional cost, this cost will be even larger than the time that you need to calculate each token sequentially, so that we don't think that token level is easy to do this adaptivity. And in comparison, we find that other inference time method or just the other maybe post-training method, they will focus on maybe we call it semantic level parallelism, which means that you have two subtasks tasks, and each contains so many tokens, but you just parallelize these two subtasks at the same time instead of just parallelize some tokens in the same task. So that we will find that in each subtask, if we think that this subtask is something can be done in sequentially, we will never parallelism them. Instead that
I want to ask a question.
yeah.
So I wanted to understand the problem correctly. So like you have an input of 5 token, let's say, and you want to generate one more token. And so instead of generate only one token, you want to generate token 6, token 7, token 8 at the same time. Is that
Yeah, that's right. Yeah. And I think that the different things is that if you consider about you have a ground truth generation, that maybe contains token 0 to token 100. And what diffusion tries to do is that it try to maybe generate, for example, token 5, token 6, token 7, something at the same time. Although they can maybe at the same time generate token 5 and token 20, but currently I don't think diffusion model shows that they have a very good consistency in very long range dependency. And for the semantic level, what we mean is that, for example, there is one subtask from token 5 to token 20, and another task from token 21 to token 40. And we just parallelize these two tasks, which means that we generate token 5, token 21 at the first time step, then token 6, token 22. They are just two separate generation things. This is what we call it to be some semantic level parallelism, because that whether we do not consider whether two tokens can be parallelism. We only consider whether two maybe concept or two sentence can be parallelism. Yeah, and we just plan it before it's actually be generated. Yeah.
okay? So can you give an like concrete example of what kind of input like a tech example would be better.
Yeah, let me see. We can go back to our demo. Yeah, if you can, yeah, further see this demo. Yeah. Yeah, you can see that in this demo that we can use this example. It's about this is a math problem, and there are maybe three things. It's about when you begin to do some math problem that you may always need to recall some formulas. Yeah, because based on these formulas you can form some results, and you can see that in our method that we just have three outlines that related to three formula. And because each formula is separate, so that we generate each formula at the same time. Just I think that uh, I think this is just what is example that we have. Just means that this is the semantic level that we just want to generate each formula instead of just consider, for example, whether weight but can be generated at the same time. Yeah.
Let's see.
Yeah, is it clear? Yeah, if it's clear, I can move on. Yeah.
I don't. Well, I can you go back? I'm not very clear yet. Sorry. Kind of
Yeah.
new with it.
Yeah, was your question? Yeah.
Basically,
Hello,
you
sorry.
say. Oh,
Sorry.
so you're saying that you generate 1, 2, and 3 at the same time, but I would suppose that you need one in order to generate two. Because if you don't, like, for example, you don't recall the error formula and the relation, then how can you know that you need to Heron formula? Like, why should I use a Heron?
This case is
Yes,
just means that before you just I think that it depends on the task. Just not we why we show this case is about using it's about these three formula as something that before the model generate each of them, the model can know they need these three formula. Just means that not the model generates the first formula, then it knows the second formula, and then it knows the third formula. It's just the model at the beginning, it's already know that to solve this task, I want to first retrieve or recall three formula. Just means that there is no dependency between the first formula and the second formula. Yeah. Yeah, because that you see that if you only want to recall the Heron formula, that the Heron formula is have no relation with the area formula, so that you do not need to have the area formula. You can just get the Heron formula. Yeah, they have no dependency. Yeah.
Yeah, but I don't understand why the model knows they have no dependency. Like, why is already no?
This is just fit down by our training. Yeah, we have such data, teach the model to learn that there's just if you know that there are something independent, you can generate them. Yeah. Yeah, I think that we will talk about the training details later. Yeah, I think that we can move on for now. Yeah.
Yeah, thank you.
Yeah, and we mentioned that for current modeling method that they mainly work from the token level for diffusion model. And in this work, we'll focus on how to make the semantic level that before, because that we think that they can be easy to be adaptive. And we want to show that how we can enable this ability within one model architecture instead of just doing some inference time tricks. So that we first want to analyze that what is needed if we want to enable this ability. As our analyze before that, we will find that even we, for example, here is just an example from the tree of thought. The left is something that self-consistency or maybe some best of them or maybe majority of them. The right is the tree of thought. We'll find that they also do some parallelize that in the generation that by splitting the input into several separate branches. But you can see that in each branch that because it's still autoregressive models, so the generation is still something sequentially. So our first thinking is about we only need to enable the model to parallelize its generation at very few steps, just like these steps, and these steps. And this is can be supported efficiently by the prefix caching, which means that when you split into some passes, you can just use the pass KV cache instead of just recompute it. So that we don't think the computation steps will be used for many generation tokens. And the limitations of this method is about they do not have a good way to merge the answer. Yeah, both these methods that they will do something like majority voting or just some heuristic way to combine the results. So an autoregressive model have no ability to combine the already have the ability to parallelize its generation. We only just need to want to make it more adaptive and but it do not have the ability to merge its generation. This is some new ability we want to enable. But for both ability, because both most of the generation step is still autoregressive, we think that it will be something easy to be modified from existing autoregressive models. So this comes to our solution that I will first give an overview of our multiverse. It is a method or a new modeling framework based on the map-reduced paradigm, which means that to enable the parallel generation that we discussed, it will incorporate the two more stages, the map stage and the reduce stage. In the map stage, we will split the current task into, for example, two subtasks here, and this subtask will be executed in the same time. And after these two subtasks are finished, we will merging them results together that use the model itself will merge it without any external heuristic rules. And finally, based on the analyze on the two passes, we will come to our conclusion. For example, here is the left is equals to the right. It requires the information from the both passes. And here I'd like to give some, we first can compare that we discussed autoregressive model, they cannot generate in parallel. They can just solve subtask one by one. And for diffusion model, we mentioned that they just brute force the parallelize everything. So we will find that when everything is masked, that you can only, for example, generation subtask one and some weight, but for some things that because they have some logical dependency, you cannot generate it. It's hard for a diffusion model to accurately learn that what to generate and what not to generate, and that will waste a lot of computation on these tokens being remasked. So that we think that our method should be something enable adaptive and losslessly parallel generation. But what we need to note here is that we think that multiverse is still only a proof of concept for now. Just means that because we only do some supervised fine-tuning, so please do not expect too much speed up on the current method that I think it only maybe offers a speed up of 1.2 on average of the current reasoning task instead of maybe some probably some degree of maybe 2 or 3, that this is something that we need to explore in the future. So when we talk about the overall concept, that we come to the more degree concept questions, that we know that what kind of model we want. We want a model to parallelize and merge its generation, and then we have several concrete problems. The first problem is about if you see the past method based on the repeat sampling. For different passes, they just based on the sampling randomness to generating something different. But in our case, we will expect it, for example, the first branch will definitely solve task 1, and the second branch definitely solves task 2. Just means that how we can ensure that these two branches can generate something different. Just if we just initialize them with the same prefix as just repeat sampling, so that they cannot be controlled to execute two different tasks. And we provide a very simple solution because as we mentioned that their generation is depends on their prefix, so that if their prefix is not complete the same ones, they should generate different subtasks. So that we introduce our map stage, which means that in the map stage we first have XS, which means that we will first sequentially write some outlines for each task, and for each subtask it will have its own prefix, for example 1 or 2 or 3. And after we have this prefix, we will split it into several branch, and for each branch we do not directly add it to generation. Instead, we will just preview its index. For example, for the first branch, we just prefix 1, and for the second branch, we just prefix 2. So that based on the index, these two branches can see the past outlines, so that they know that they are paired with task 1 or task 2, so that they can generate its own task without conflict with each other. So that this solves the questions that it can ensure some difference between different passes with a different prefix. And the question 2 is about how to merge the information from different passes. This feature is very important because that we don't want the model only to see some summary from the past information, and so that there will result in two problems. The first problem is that for example, if there are some important information in the middle of the context, if you just transfer some text, that you will missing these important internal model states. The second problem is that why we call it a modeling is about if you consider you just summary each passes and just refuse the text into the model. The problem is that during the training that the refilled text have a different KV cache with the original one, so that their information cannot be exchanged, so that no gradient backward is allowed in this case, so that you cannot optimize your bump stage with your merge stage. So that what we want to is that we want to have some ways to merge the information from the internal space. So this based on this concept, we introduce our reduce stage. In the reduce stage, if you see this formula, you can see that you can see that if you want to generate XE and maybe the future X3 and X4, they are conditioned on the both passes instead of a single passes. This is some modeling that different from the autoregressive models. Just means that it can see KV cache from all past passes instead of single one branch. So that we think that if you can see all this information, you should access to all past information, and there should not have no information loss. So that this is how we merge information from the different passes with no information loss.
Maybe you'll get to this, but I'm curious how it attends to those different sequences. Like, do you throw them all into a big self-attention matrix, or?
Yeah. Actually, that we use modified attention that with a customized attention mask. I will talk about this instantiation later. But I
Sorry.
just want to first say about the conceptually that you just want to access both KV cache or model states from different passes. Yeah, so that you can access all information. Yeah, this is what we call no information loss. Yeah. So that after these two questions, conceptually that we have a model, it can have split into different passes for different tasks and merge the information from all passes. But the problem is about how we can aware that we need to shift between different stage, because that we can see that in comparison to the autoregress generation, currently we'll have map stage, process stage, and reduce stage, so that the model needs to adaptively shift between them. We get inspired from the domain of the, for example, the compiler or just the interpreter. It just means that we want to signal the model, the different stages with some special tokens. I think that this is something that people usually know, you use that when you use tools these days in the agent domain. Because that you can see that, for example, for the reasoning task, many previous works that even the DeepSeek that they use the sync and answer to separate their answer stages. And we have designed more complex structures. We can maybe show some examples here. First is about when you want to do some parallel, you will first start with a special parallel token. This is just indicate about the whole block, that is a block contains some the map phase, process phase, and the final reduce phase. And after that, you will first output a goal token. This is just the starting point of the map phase. And in this phase that you want to output some outlines of each subtask you want to solve. Yeah. Yeah, we have next processed phases in our demo. We have show it here, and we will talk about this later. Yeah, actually, we mentioned the next structure here. Yeah, and for the second outline, that I think that so that you can see that the model just brute force just briefly input two outlines sequentially, so that and each outline will has its own index. And after that, after all outlines are output, the model will just generate end of the goal to signal that the map phases has the end. After the map phases has ended, that we come to the process phases. Because that when we know that here we have two outlines, so we only want to initiate two separate passes, so that we have pass 1 and pass 2. And after that, these two passes will be generated in parallel until it's come to its own end, which is signated by another special token which indicates the end of the path. So that each path just solve its subtask and wait for the different passes. After both of the two passes are finished, we come to the reduce phase. Actually, that if you just finish two passes, you merge them and you can continue to generation. But we still introduce the reduce phase, because that we think that the information from different passes do not connected. If you directly move to the next step, the model will tend to maybe a little confusing. So that we want to explicit a reduce phase that by starting with a conclusion token. Just means that in this phase, you need to maybe conclude the information from these two different passes. And after you end your conclusion, you just you output end of the parallel token, which means that the whole parallelism has been ended. Therefore, we think that this is just a well-defined with triML structure that automatically control its generation flow, which means that your model generates some special token, and your engine will be signated by this special token. And after that, it can generate, it can change its phase to generate go beyond the autoregress generation. And we can easily see that if in each single path, it's called another parallel here. Some nested structures is natively supported in our model. So we talk about many things about modeling framework now. The modeling framework is good that it can enable a very flexible parallel execution based on the map-reduced structures. It can be nested, or maybe consecutive, and it can maybe cover different cases. But the problem is about how we can have some parallel data, because this requires a very well-defined structure, but we only have unstructured data in our real-world models, because that currently we only have autoregressive model. The first finding is that we find about although currently the model output or chain of thought they are generated by some autoregressive models, but they are actually something containing some intrinsic parallelism. Here I show 4 examples here. These examples are from both either the Gemini 2.0 or just the example from DeepSeek 1. We can see that in some generation steps that, for example, the model will output case 1, case 2. Yeah, can we Yeah. I think that for the questions that can you have nested process phrase and can we repeat the MapReduce procedure within a single generation? I think both is supported. Yeah, maybe we can check more time about our demo. You can see that in our demo, we first have one parallel structures, and in this parallel, there is no nested one. But after this, the model just directly open another parallelism just within just only a few interval between them. And in the second parallelism that when it do parallelism, it finds that there are some nested structure. So it continue to call the parallelism. So both nested and the repeated structures are supported. Yeah. Yeah, let's go back to the previous slides. Yeah. So that we can see that the first case is about a case study, and the second case is about analyzing a very complex system, which can. And the third, we call these two kinds of the collective branch because that in these two cases, that the information from all branches will contribute to the further generation. And there are another cases we call it something called as a selective branch. It's just about maybe for example it's just start from n equals to 1 and then it consider to n equals to 2. Maybe some passes there are some wrong answers and do not contribute to the final answers, but you just need to test some case. And finally, it's just maybe test the different solutions to our questions that you can see that this is the output from DeepSeek R1. There are many weight and alternatively. And here are some affiliates attempts. And these attempts are not important, are not contribute to the final answer. But if we can also parallelism them, that we can try different solutions at the same time. So our first observation is about this such of the intrinsic parallelism is commonly existent in the reasoning task. And we typically classify them into two categories, which means the first thing that what we talk about some collective branch and selective branch depends on whether all the branches contribute to the further generation. And another thing that people have asked is about whether we enable some more advanced structures. Here is an example of consecutive structures, which means that we repeatedly call two map stages that after one by one. And this one is another case is about one we call a map stage within another process stage. So that we mentioned that our structure is very flexible to cover any things that can be represented in maybe a nested or just a recursive or consecutive MapReduce structure. Next, we further analyze maybe the occurrence or the frequency of different types of the parallelism within each single chain of thought traces. This is generated, the chain of thought trace is generated by the S1 team because that they have some ones from DeepSeek 1 or Gemini 2.0 Flash. And our first observation is that when the model tends to generate a very long answer to a very complex question, that its reasoning traces always have some parallelism. We will find that in our analysis, about 98% of the output have some intrinsic parallelism based on the analysis of the Gemini 2.5 Pro. And we also calculate the average frequency of in each example. We will find that in both cases that the Gemini thinks that there are average 7 times in each generation. So that this means that there are a large amount of parallelism in each example. Additionally, we further analyze about the ratio of different types of the parallelism. We will find that for the majority part that it's being consisted by the collective branch, including both case study and subtask execution. I think this is very reasonable because that we just maybe split from one single chain of thought traces. So there should not exist so much something like uncertainty or repeat sampling, so that most is still collective branches. So that this just provide maybe all our information about what is our training data's parallelism feature. But the problem is about we have this intrinsic parallelism, but we have this, but they do not have the structure, and we want to generate the structure by ourselves. It is hard to, for example, generate manually, so that we want to prompt a large language model to generate such structure. So our first attempt is we try to prompt the Gemini with under the DeepSeek R1 to with hints of these structures to let it to directly think following our structure. But the problem is about the model is actually doing autoregressive generation, so it seldomly outputs the structure. Here we provide a comparison between the implicit and the explicit parallelism after we hint the model with our structure. We will find that within the analyze that each we will have a very diverse number of the parallelism within different examples, and they typically have a number larger than 5. But when we ask this one is DeepSeek 1 and this one is Gemini 2.5 Pro, and when we ask it to generate such parallelism, the problem is that they cannot actually transfer this intrinsic parallelism into explicit parallelism. The DeepSeek R1, they cannot follow your instruction, do not generate any structure. And for the Gemini, it maybe on average generate only one structure. So that we cannot directly prompt the autoregressive models to generate the structure we have desired. To further analyze this question, we further conduct a probing test, which we actually do is that because based on our analysis, we know that there are some steps can be parallelizable. So there should exist one token between these parallel steps. We just take this hidden states away with some another hidden states to form a pair. We want to just pass this two-layer MLP to understand that whether if we will train this two-layer MLP, whether the model can classify that whether this hidden states is just at the time step that you need to split your task or just not at this time step. And what we find is about the model do not aware that when it should split its generation based on the information of this hidden state, because that we can see that when we want to predict this time step that it's always output and accuracy just near 50%.
I just want to clarify. These are models which weren't designed with this kind of parallelism in mind, right?
Yeah.
Okay, so it's not surprising that you can't find a probe that works for identifying potential parallelism in their systems.
Yeah. Just means that I
Cool,
think that
cool.
we just find some intrinsic ones. Yeah. But based on the attention patterns that they do not aware of this parallelism. Yeah, just the model do not find this. So we hypothesize that this is because these parallel branches, they are just some generate because that the model is learned from the human text. So human will write something that can be parallelizable in a sequence because human cannot do parallel generation. So that they just learn these internal parallel patterns in the data instead of actually understand that there are some time steps you can do things in parallel. So that this just bans our possibilities to just directly let model to generate the structure we desired. So we come to another solution, which means we just try to rewrite the unstructured chain of thought trees into parallel ones. I have provided a very concrete example here, which means that at the first step that we will have inherent parallelism in the original reasoning chains that, for example, here is analyze different primes. But in this case, no structure is available. And to enable to incorporate our structures into this model, we just have our 5 steps pipelines. The first step is about we will first pass the chains into a tree structure summary. This is answer the questions about before that people are curious about the nested structure, and this is the reason why we just calculate a tree structure summary, which means that we will first split into steps and then we come to some substacks. So that based on this two-step split, we can have some nested structures. And after these 2 steps that we have a tree structure summary, we want to further identify that, for example, whether maybe step 1 and step 2 they can be parallelism, or whether maybe step 2.1, 2.2, 2.3 can parallelism. So that we just let the model to analyze that which steps or substeps can be parallelism, and will output a plan of it, something like the step 2, step 3, that they can be parallelism. So that we will have both the plan and both the split of the reasoning chain. After that, we will just reformat our summary into a maps reduced structure. This is very easily done by insert a parallel and the end of the parallel between each parallelizable steps. Here we can see that we parallelize step 2.1 to 2.2 and step 2.3 here. Here is just a sub-step parallelism. And anotherly, we also parallelism step 4 and step 5. Just based on this parallel token that we know that which part can be parallelism. And for the fourth step, that because that every previous operation is operated on the summary space, so that we want to go to the original reason chains to provide the detailed information. So we just refill the full detailed information after this step, so that it will form something that only have the parallel structure. And finally, we'll add our map and reduce stages by let the model to write its own outline and conclusion. And we also rewrite all passes to ensure that different paths should be something totally independent, because I think that for the details that you can refer to our appendix or maybe our code, because that we have released all of the prompting code that you can just try with your own Gemini 2.5 keys. Yeah, but we want to mention that we have many important maybe experience or failure that during we try to modify this prompting framework. The first thing is about why we split into several tasks instead of directly input the model with a very large task, because we find that the task is very complicated. So if you want to fuse several tasks into our prompt, this will dramatically reduce the accuracy. Just means that the model cannot write the context in a good way. The second thing is about, I think it's a common problem of the current large language models, is about they are not good at copy paste, especially when our cases we want to copy paste a long reason chains contains more than 10,000 tokens, so that they will tend to maybe limit or just ignore some sentence when you try to do such copy and paste, because that they just want to be lazy. So we find that if you want to the model to follow more of your instruction to copy all the sentence that we just mentioned many times about the sequence by sequence in our prompt, and we find that this is very helpful for model to see each sentence during its thinking processes. Moreover, we also restrict the edit distance to a smaller value that below 0.2. Just means a compression about the distance you need to edit compared to the max just generation length. We want to avoid skipping too much sentence. Just means that you need to very fine-grained checks, because that LLMs, even the most powerful ones, they are really not good at copy and paste. And the third thing we find is about why we need to rewrite the parse is because we find that the recent LLMs tend to have words somewhat like similarly or just alternatively, or use some cross-reference in different passes. So even if the meaning of different passes should be something irrelevant or independent, but if you just keep its original tone or original words, that it should be something have dependency on the text level, so that we will ask our assistant large language models, which is Gemini 2.5, to rewrite each path to avoid such problems. And we find that after we incorporate so many details and split it into really a huge prompting framework, if you see our appendix, that we just spent maybe 5 to 6 pages for our prompting framework. And we find that at this time, most of the data quality is preserved. But if you directly, yeah, let me check. I note I noticed that the different branches share the position. I think that for the position ID that I will talk later in the algorithm part. Yeah, I will first finish the prompting. Yeah, so we just want to mention about after rewriting that the data quality is still slightly reduced, and I will maybe talk some our hypotheses about this later. But I think that it only reduced maybe 3 or 4%, and we still mix it with the original sequential data for some better performance. How to rewriting is still maybe a problem that if we want to enable such structure. And previously, we talked about how we generate such data, and with our both mixing and our data creation, we will have some structured data that can be used to train our model. But what should our model we should have? It just means that previously that some audience that ask about our method based on self-attention. Actually, it is yes, because that we need to instantiate our modeling in a detailed architecture to enable this ability. And we actually definitely we choose the more famous the transformer layers or the attention layers, and provides a variant of the attention layers, which is not the causal attention, to ensure that different paths in our case can be executed in parallel. We mentioned this is not very hard to achieve because it requires two things. The first thing is about for different paths, you do not let them to see each other. Otherwise, they cannot be generated in parallel because they have some relations. So the first thing is as we modify the attention mask, which in this case that different paths they cannot see each other. You can see that we have some empty paths here that from path 1, path 2, path 3, and path 4, and they are just mask each other so that they have no relations. Only the conclusion can see all of them. And the second thing is about we need to do some modification about the position IDs because that for the current transformers that they are mainly based on the rope embedding, so that if you different passes they are start from different positions, you cannot parallelize them during your inference time. So that we modify the position IDs that different passes starting from the same position, and after we end all passes, the conclusion will starting from the maximum value of the position from all passes, because our different passes will have different lengths. So we ensure that the different passes, we ensure that there is no negative relative positions. But maybe a slightly problem here is about, for example, if path 1 is very short, that it will have a long distance with the conclusion in the position IDs. Yeah, but actually we find that this is not a very huge problem. So we mentioned that multiverse is that if you see this attention mask, because that we think that attention mask always provide many rich information, you can view multiverse in another understanding way. It's about it's actually let the model to decide its own sparse attention pattern. Yeah, let me see the question. First is notice that the different branch share the position encoding. Do you have some process like controlling the temperature similar to app, or to make sure the conclusion process work well with the shared positions? Actually, we do not incorporate the temperature or some additional hyperparameters in our previous work, because at this time we directly train the model with this new position ID and attention mask, and we find that because that is similar to the previous causal attention with a slight modification, we find that it can generalize well that with only training on maybe 1,000 examples. But I think that we can test on some maybe more synthetic tasks to see some strict case. I do not test on this. And the second case is about can we integrate the selection and the collection functionality to the reasoning framework directly, thus eliminate the rewrite via the assistant large language models completely. Oh, I think the reason why we incorporate this is about we mentioned before is we have a specific structure, and what we really want to do is we want to generate such structure. And before we do this, we actually try to maybe teach the model that there are some structures that you need to follow them and to generate in this way. But we find that in both zero shot with some instruction and some few shot settings, our model cannot correctly generate these structures, because the model itself is still autoregressive model without any modification. I think that if you have a very strong multiverse model, you can definitely let itself to generate such structures. But currently we only have the autoregressive model for pre-training, so we need some rewriting. Yeah, I think this is the main reasons. I'm also very curious the case when the path length varies a lot, will the performance be influenced? The starting point of the conclusion is from the longest path. I have talked with maybe some other groups that are doing the similar directions, and I think the most things is about we think that a good thing is about we do not see much difference on the performance. Yeah, because this is the only mechanism we can support now. Yeah, and what we find is about instead of the more nearby positions, maybe far position are the same for the later generation. So I think that this is the reason why we include the conclusion stage. We just want to the conclusion stage to recall some information from different passes. So I'm imagine that the only case that if let me think how to say it, just means that if you not actually want to retrieve some very exact information from very far passes, and there are some maybe noisy from the recent positions, I think that this is not a huge problem. So this is means that in real world task it seldom happens. The position seldom cause problem, but I'm not sure about synthetic task. If you just make some manually create some tasks that it will have some conflicts on the different passes, I think that it may still have the possibility to confuse. But I hope that our fine tuning fix it, but I'm not sure about this. And we next, yeah, you can ask.
So it's clear in this attention diagram that you have up on the screen how the merge occurs in the case where you have this three-way split.
Yeah.
When you have more complicated nested merging, do you have correspondingly more complex attention masking?
Yeah. We will just yeah, for the nested one, it just means that for example, it's in this blocks, we will form a nested some attention mask similar to this. Yeah. Just means
Got
that
it.
if you go
Thanks.
to the next level that you will have yeah, we will always create such data. Yeah. Yeah, and we want to talk about why we design it in this way and why our modeling is have some very amazing practical advantages. We talk about two advantages. First is about as we talked a lot, it can be represented by this attention mask and the positions. So you can see that it can be trained in parallel using some customized attention masks because that you can the SFT or just a pre-training, they are something different from the RL or just the generation. It's not online rollout. So that you need to parallelize everything to enable a efficient training, and this can be achieved in our method with a customized attention mask. The second thing is about because that it is very similar to the original caution mask, only shift about some position IDs and some shift about some more attention mask. You can actually convert an autoregressive model into a multiverse model with just training on a few examples. In our test cases, we only do it with 1,000 examples and learn both reasoning abilities from data and transfer the model architecture, and it successfully achieves it. So that it is both training efficiency and the data efficiency. This indicates that created multiverse model can be cheaper because that you do not need to do any pre-training. You just only need to do some fine-tuning or continuous pre-training. And so you can try it on existing leading open source AI models to create your own multiverse model for your own task. So that I think that this efficiency is very important for us to adopt some new architectures into real world challenges. Because that if you only train some small models, people will concerning about its scaling ability. And for the two that we have solved the data and the algorithm, and the final problem is about how to actually generate in parallel. Because that if you think that you just have trained a multiverse model and you just loading it using Hugging Face or sklearn or via any inference engine, they are all inference engine for the autoregressive models, so they cannot actually generate in parallel. This is so finally we also create a real world inference engines that to support our multiverse models that we call it a multiverse engine. It is based on sklearn. It's just because that at first that we will have an interpreter. It will at a different stage that we will detecting the special tokens and we will recording maybe the outlines and then we will detecting the end of the stage that we shift the stage and prefix some passes, and then we start starting parallel process. And then finally, after process is finished, and we just starting our reduced phases, which means that we just incorporate interpreter into the original SGLang generation with a dynamic shift with prefilling and decoding. We can enable our model to just dynamically shift between two modes. So we mentioned that this feature is very good because that you can actually use this feature to adapting your multiverse model to existing autoregressive engines. It is not a huge process. We only take maybe 2 or 3 weeks to do this modification. And we mentioned more things about why we choose SGLang instead of VLM due to 3 reasons. This is not we are not the fans of SGLang. We just think that it's more suitable for the multiverse. The first thing is about because you can see when you do this task split that you have 2 passes. So one core efficiency gain of multiverse is actually come from the prefix sharing. So we mentioned the radix attention in SGLang is very suitable for multiverse. This is the first reason why we have the radix attention. The second thing is about SGLang enable some continuous batching, which means that you can feel free to switch between different stages. This is the second reason. And for the last reason, it's about for different passes because that you need to allocate some new memories or separate memories. So a very good thing is about SGLang supports the page size of KV memory to be 1, so that even if 2 passes generate different lengths, when you concatenate them together in the reduce phase, you will do not need any padding or some customized attention mask because the page size is 1, so that you can directly connect them together. So based on all this, we have both the data algorithm and the system for us to have a multiverse. And then we comes to the training of our multiverse model. First is based on our multiverse creator, we first generate multiverse 1K by rewriting the reasoning traces. Typically, this can be done in something like 1 day because that we do not use much API. And I think that if you have more, that you can generate faster. And then we what I want to further mention is about why we use these trees, because that we find that DeepSeek R1's data is more better than the Gemini and Cloud when you distilling a small model, 32 billion. We guess that this is because that if the model says just has become one is too huge and one is too small, you cannot expect small models to think the same as a very large model. Just means that the distillation used Gemini is not very good. This is the reason why we choose DeepSeek R1. And after we have such data, we will perform supervised fine-tuning with our multiverse attention. First, we will find that before training on each example, we will first generate our masks and positions by scanning the context from left to right. We will have some stacks to store the current stage so that we can, based on this, to scan the edge from left to right and to create the attention mask. This can be done like some, this can be further acceleration if you consider to pre-process them before training, but actually this do not take much time in comparison to the training, so it's not a huge cost. So typically that our training is conducted on 8B200 GPUs, which only takes 3 hours, which means that only use 1 day and 3 hours. You can have your own multiverse model that very easy. Yeah.
Hi, Xing. May I ask that how much data do you have in total that you collected in order to train this model?
Actually, that we have 1K original data and 1K modified data, and we mix them together, and we in total we have 8 epochs, so that the total training data is only I think 8,000, and each the token the length of token is something that more than 10K but smaller than 32K. Yeah.
Okay, thanks.
Yeah, and continue to this question that we actually train for 8 epochs, and we have a mixed ratio, which the mixed ratio is the first 2 is always autoregressive data, and the third one we introduce some multiverse data, and then half, and finally we only have multiverse data, because we find that it is very important to initialize with some autoregressive data that if you directly use the rewritten data, it still result in some performance drop. Yep. and we just form a pair of each example. So for this 0.5 and this 0.5, they just use different examples. Maybe the first half from the autoregressive and the second half from the multiverse for the first epoch, and another one for the second epoch, so that we can ensure that we use different data for these symmetric epochs, so that we further try to separate the prompting of both the kinds of data from different sources to let the model have some controllability of its generation process. For autoregressive models, that we add something like think step before answering before its answer, and for multiverse we add think step and in parallel before answering. But from our experience, we find that this just slightly improves the degree of the parallelism during inference. Therefore, we don't think that this is a very good way to control the behavior from autoregressive model and the multiverse model. That I think that more ways can be explored along this controllability. And finally, that after we have our model and these things, that we have our multiverse 32B and we test its real-world reasoning ability. After supervised fine-tuning on our mixed data, we will find that it dramatically improves the performance of the original Queen model, that by maybe 24%, and the performance is on par with the autoregressive model, which means that even we change the model architecture, the quality do not drops. We can see that in both AME 24 and 25 that we have some leading results comparing with the currently leading autoregressive models, and it is a very huge value. Yeah, but we have to emphasize that you can see that we do not have a very large degree of the parallelism, so this is something practical that we should not result in much performance drop. I think that this just validates that multiverse is a reasonable modeling framework that can work for every task, but do not mean that if you further increase the degree of the parallelism, that how you can maintain your performance. Yeah. And because that for this analyze that we are without no budget constraint, just let the model to generate as longer as it can, so that it do not show maybe what is the efficiency gain of our multiverse, and so that we further conduct some evaluation on the GPQA and mass task, because that we find that these two tasks are most sensitive to the context length, and we try to set a same maybe generation length or time to different models with different checkpoints with different points here, and let it to generate. And we will find that multiverse always show better test time scaling with the same generation time comparing to the autoregressive model, because that's actually that we can generate more tokens at the same time. So we should have a better performance. So I think that this demonstrates that the potential of the multiverse, that if you can further scaling the number of the parallelism, you can achieve more performance gains at the same time step. Yeah, but this is that we need further exploration. I think that I missed one page. So yeah, maybe I can let me just shift. Yeah, I think that I maybe missed the efficiency analysis. Yeah. Let me directly shift the slides here. Yeah. I guess that I can. Yeah, I guess that I missed that page. It's about we also further checked about the practical efficiency of the multiverse. It's about we split into three regions. In the first regions, there are many data points, which means that there are many data points that fall into this part during our real generation. As it currently that the parallelism can be generally achieved by our multiverse model. But you can see that in the second area, we can also see some data points that have some parallelism degree of 2. Just means that multiverse can actually generate 2 more parallelism, but based on the task and based on the training, that we do not unlock this possibility. And after that, we have some extended lines. We just want to show that if you have some tasks can be really parallelizable, and you have a mechanism to parallelize this task. It's in most settings, you will actually get the low latency for each tokens with the better scalabilities with the increased parallelism. I think this is a different, more efficient way of the scaling. And for the second figure, we just want to show that which is the same as what we have in our slides. We want to show that with the increase of the bar size from 1 to 128, which is still some regions that within the IO bound that just the speed up is linearly with a degree of the parallelism. Yeah, so that we just see that our model not only for the single batch, it can generalize across various parts. If it's maybe just too not too large, that's something that beyond 1K. Yeah, I think this is all things that we have about the multiverse. Yeah, and that will be very interesting that in the future that if we further consider the reinforcement learning or have some better algorithm, I think that multiverse is just only the first step that we want to unlocking some parallelism that on existing auto-recursive models without maybe some new modeling paradigm that directly starting from the pre-training, so that even large companies, there will should be some people that try it in a very fast way. Yeah, I think this is maybe just all for today's information. Yeah, and for any questions, you can directly ask me or just share in the chat. Let me answer one question first. The first is about the scaling curve looks good even the number of the parallelism is below 2. If the parallelism is increased to higher, will the accuracy reduce or increase? I think that currently that because that we are based on the R1 reasoning traces, so it is there are existing many sequential steps. Even we try to parallelize everything we can parallelize, so sequential is still bottlenecked, and we have tried it to change some prompt to increase more parallelism, and we find that actually that we are not sure whether it's a problem of data or just another problem, but currently that they will definitely reduce the upper bound of your model, so we only keep a parallelism degree of 1.2 on average for now. Yeah. Yeah, feel free to ask any questions. That yeah.
Yeah, thank you for the great talk. I was wondering, like, the number of branches is decided by the model, right?
Yeah, this is the reason why we had the outline stage. Just means that we want outline stage to sequentially output. Let me find it. Yeah, just means that just means that we want the model itself to generate a very short sequence for each subtask, so that the model can follow it. So there is additional overhead, yeah, but generated by the model itself. Yeah.
Yeah, I see. So, before generating in parallel, you kind of need to, your inference engine needs to switch from the sequential mode to the parallel mode. And so that means that the inference engine needs to like, does it parse, does it count the number of outlines?
Yeah. Actually, that it will just record the number of the outlines to decide how many outlines that it should generate, and moreover, in addition to record the outline, it also just extract the prefix of each outlines, because we find that the models that sometimes it generate 1, 2, 3, sometimes it generate 1.1, something like this. So we just like the model to copy it, and after it's recording all this information that. We will definitely switch between sequential to parallelism that by just we will add 3. For example, in this case, we will add 3 new requests, and for each new request, we will prefix with pass 1 and pass 2 and pass 3. Just means that it will request switching between the decoding to prefueling and then go back to decoding. Yeah.
I see. Yeah, so the count of the outline token, outline tag, and the prefix is done like on the fly when generating the outline, right?
Yeah. This is on the fly. Yeah, because we cannot predict it.
Cool. One final question. Do you guys do you guys treat the outline, those special tags as extra tokens, or by updating the tokenizer, or you just reuse the existing tokenizer and just treat them as plain text?
Actually, that I think that I use maybe some tricks that mixing that this is generated first. We will initialize some new tokenizations about these special tokens, But what is different is about the previous when people initialize a new token, they just use the average of all past tokens in the tokenization tokenizer. But what we find that this will result in sometimes that you generate some wrong tokens because we only train on very few data. So we actually do is about, for example, for this parallel tokens that it is a new token, but its original embedding is from the original parallel token, not special one. Yeah.
I see. I see. Yep. Thank you. I appreciate it.
Yeah. Thank you very much for your question. Yeah, let me. How do you see the advantages of the multiverse compared to the traditional multi-agent approaches, such as using separate models for goal generation, path finding, and reducing passes to a final answer? I think there are two advantages in comparison with the multi-agent system. The first advantage is about in the multi-agent system that you need some external workflow, which means that whether some task can be parallelism or not parallelism is just I think that it's hard for you to maybe in the middle of the generation model self-aware that it's a time to do the parallelism and output such plan. I think this is the first challenge. But the second challenge, why we called it native, that I think that recently, I think maybe in the May or someday, there's one paper called about maybe something why multi-agent system failures. It analyzed many failure cases. I think one problem of the multi-agent system is about you can actually do the generation in this style. But the problem is about after you merge some things, you transfer you are just communicate on the text space. So you cannot have access to the past KV cache of the past model, so you lose some information. And the more important failure we guess is about because that do not use the past KV cache, you only use the text, so that you cannot back propagation directly on the hidden dimension that use the supervised fine tuning. So you cannot based on the after reduced stage to decide that whether the map stage that splits the task incorrectly. We think that this is very important that if you have a very large system and you want to do some end-to-end optimization, we think that RL still a little slow and our multiverse can combine everything in one model so that you can do some end-to-end optimization, use just supervised fine-tuning so that this can learn these new patterns very fastly. I think this is the main advantage. Yeah. And I think that there is also another advantage is because that in the multi-agent system that you actually need to implement a very complicated system or just combining many engineering work. But in the multiverse that you only need one rule. Yeah, and then you just need one engine and let the model itself to decide how to generate it. I think it's much easy to the implementation and resulting in less errors. Yeah. Oh, I see this. I just wonder if just introducing a higher level of reasoning plan or structure, you can achieve a better outcome in terms of the reasoning benchmarks than just of the plain chain of thought. I think this is the reason that this is one problem we are facing previously because we also want to try to know that what is maybe the optimal way or the most efficient way to solve a math problem with the maximum degree of the parallelism. But the problem is about the currently reasoning traces, especially the one generated by DB1. We think that it's very noisy, just that there are many tokens like wait something or many recheck steps and you do not know that if you remove them, although you think that this is a correct answer, but it may hurt the problem. So I think that this just means that actually I think if we have a higher level reasoning plan and structure, it should have something that at least have a better trade-off and maybe some better performance because that we can isolate maybe some different test cases, avoid some maybe interaction between them. But I think in the current reasoning trees, the practical problem is how we can get the more brief reasoning chain that can achieve the better performance. I think that we do not have evidence of it. So it is a problem of the empirical evaluation. Yeah.
Actually, I'm curious to what limit to the upper bound for this pattern, because it looks like in the map stage there is a planning or like a drawing outline process, right?
Yeah.
And in the reduce stage there is a conclusion stage. I think maybe this point would be very important for the performance, right? I mean,
Yeah,
uh,
I think
yeah,
that yeah.
yeah, both
Currently
of them
that
have to be the bottleneck, right?
what do you mean by bottleneck? Yeah.
For example, if a model cannot like draw a planning at the very beginning quite well, maybe the parallel generation cannot provide very high quality like
Yeah, that's right. Yeah, that's right.
cache states, right? For your redundancy, right?
Yeah, just means that if the model, for example, it generates a wrong plan, maybe some, for example, if one subtask is related to another subtask, just this branch is just something should be just wasted. Just it do not just generate more token, but do not provide more information. So I think that it's very dependent on whether the model itself can generate some good plans. So I think it's very related to some problems that people explore in the agent domain these days, that you need to planning something and you need to summarize something. Yeah.
I'm very curious why in the accuracy, aspects, why this pattern is better than the auto-recursive with the same trained data because of the map stage or reduced stage. I have no idea which one like contribute to the higher accuracy.
I think that in the current case, because we only do the supervised fine tuning, so the map stage, although it do some planning, we still think it's a kind of fake planning, because that actually this planning is just after you see all of your generation, so it do not reflect the real generation process that you do planning before. We just think that this is just about maintaining of the structure. So we think the performance gain is mainly come from that our model can generate in parallel. So at the same time, it can generate more tokens. Yeah, I think this is the only reason. Yeah.
Oh, I see. I mean, it looks like a larger exploration space, so contribute to the performance, the accuracy improvement.
We will hope it, but let me back to let me try.
Because I have no idea whether the comparison is based on the same numbers of the tokens or just maybe you will introduce more tokens for in the generation and then achieve a better performance.
We will actually use the same latency, which means the same something like same generation length, because that we think we need to be latency driven. And for your question about a larger search space, I think that definitely will expect it to have, but I don't think it have much this ability before, because you can see that in our mainly in our analyze that most of the branches are collective branch, which means that they just execute different subtasks. Instead of maybe they are just uncertain, they try maybe 4 different kinds of the solutions. So I think it depends on the data. If you can imagine that, if you can, for example, you can collect some different passes by repeat sampling, it can maybe learn more selective branches, because you only need to, for example, select one out from them. But currently that our data is rewritten from the one thinking tree, so it's tend to be more likely a subtask extraction. I think that our structure is flexible, just means that it depends on what kind of data you have. Yeah.
Okay, what I'm talking about is figure 7. Let's recap that. Because in figure 7, you have this same budget for the comparison, right?
Yeah,
But
yeah.
I noticed even the generation length is smaller. It's more like 2K. The multiverse would be better than the autoregressive pattern. So I'm curious, I mean, whether the map or reduce that, or one of them contribute to that, or other reasons. So that's my question, actually. Sorry.
I think it's not the reason. It's just because that if we only have 2K, Multiverse can, for example, it can generate maybe 2K and 4,000 tokens. It has 4,000 more tokens. Maybe these 4,400 tokens is a key point to solve a problem instead
Oh,
of just unfinished one.
okay. So for the upper bound of the accuracy, will it be reduced? You imagine it will be reduced, right? For example, like in Mass 500, if we given like 10K budget, like will the upper bound of the accuracy be reduce the
Actually, our observation is about if you consider AME because these two tasks is very challenging. So in this task, we have a similar performance. And in the Mask 500 and GPQA that we find that on average that we result in a slightly maybe 1 to 2% performance drop. Because that I think we still modify the attention mechanism and we only train for one case or one case example. So you can imagine that our model is not at the as stable as the original as not as stable as the original autoregressive model. So when the task is easy, so it may have a better maybe it have more uncertainty and result in a slightly performance drop. But when you come to some very complex questions that this uncertainty will do not affect about the a lot about the performance. So they have the same performance. Yeah.
Okay, thanks for your explanation.
Yeah, I think there's one more question. I mean, it seems most example on master problems. How do you see opportunities that to parallelize in other texts? Actually, that previously that we as a starting point we are very interested in the code, but currently we do not do code because that S1 is the only code base we find that you can enable this new architecture with 1,000 example because this rewriting process is actually very expensive that only generate one round data that if with no maybe credit that you need maybe $1,000. So we just generate for the mass data that for the code data, I think that maybe we'll try to find some funding or to support this. Yeah, we will explore in the future. Yeah, we think that for the code domain that it should have some better degree of the parallelism, and we are also actively exploring something in the agent domain. Yeah.
Yes, could you please elaborate? I don't quite understand. So once you generate a token that you should continue in parallel, what happens next in terms of implementation? You increase the buffers and you start packing like three parallel paths in a batch. How does it work? I mean, I kind of have an idea about VLLM, but here, how you implement it programmatically?
Yeah, for the implementation, it's a kind of the batch inference with prefix sharing. Just means that, for example, when we have pass one and pass two, we can see that before the index, all information, all prefix of these two passes are the same. So during our implementation, what we actually do is that we just let the engine to just send two new requests, and each request it will prefix pass one and pass two and based on the same prefix. Just we add these two requests into our buffer to let it to continue generation. I think this is supported by the continuous batching abilities of the current inference engine. Yeah.
And the inference engine is what? It's like SGLang?
Yeah, SGLang. Yeah, because that we find that SGLang is much more flexible. Yeah, it have a better support of the Redux engine and continuous batching. Yeah.
So basically, after this fork, you start like say fork, like you need to generate two paths, then you generate in parallel
Yeah,
one
actually,
token.
yeah. Let me try to explain. Actually, what we do is about first that at this time step that we generate something that this is on one thread or one request, and after we detect the end of the go token, we will end this. We will just terminate this thread or just this request and initialize two new requests, and we will just move copy the indices of this information as a prefix of these two new requests so that these two new requests are based on same prefix and just to send to the engine for the continuous running. After that, finally, that when for example one request is ended with the end of pass, we will just send it to something we call zoom by the zoom by request, which means that we just store it into move it to another different buzzer, which means that its information will be used for later, but it's terminated now. Yeah, and finally, we'll just after all passes have finished, we just signal a new request to combine all passes KV cache. Yeah, just means that we will dynamically open many and end many requests during our generation. Yeah.
And what would be the position, encoded position for each of the requests? You just shift them by fixed length, but you don't know in advance how long would be each one of responses would be. You just have some kind of maximum length per response.
Yeah,
How
actually, yeah.
Mhm.
Actually, I think this is the reason why we use SGLang, because that we cannot predict that how long that each pass will generate. So that it's hard to maybe allocate some continuous memory that for different paths, because you can consider that if it's out of your expectation, it can maybe result in some empty space on the physical memory. But how we adjust this is about this is the reason. This is the third reason we think that SGLang supports the page size of KV memory to be 1, so that on the physical memory they are not connected. They are still some discrete into different places. But we just concact them indices to form maybe a whole complete KV cache. And we find that based on the good implementation of SGLang that use a page size of 1 do not hurt much of the performance with some maybe partly some degree of 2 or 3, something like this. We find that's still already very fast. Yeah.
But would you need a consistent embedding so there wouldn't be overlap to generate the conclusion after you merge, all the forks requests? So they shouldn't be overlapping, right? Positional embeddings for different branches. Otherwise, it would be. Or is it okay? So is it like a requirement that the positional embeddings would be different for each of the branches?
Sorry, what do you mean? Sorry, yeah, for the you mean
Like that when you encode positions, right? Maybe I'm just missing. I don't know well about rope embedding, so maybe it's not an issue. But anyways, so when you encode the position for on each of the branches, so
yeah.
you need this, every token on every branch would be different, would have a different position, right? Is it a requirement or not?
This is not a requirement. For every branches, we start from the same position. They just their starting position will be the same. Yeah. They just share the same position. This is different from the original autoregressive model. Yeah.
But in terms of attention, when you generate the coda, like after the merge of the branches, is it okay that all these tokens there would be some positions that would have several tokens in parallel?
From our experience, we find that sharing the positions do not hurt the performance. We find that you only need to, what you only need to strictly keep is about the maybe you should not generate some negative positions. Just means that a token cannot attend to another token that with larger positions. But for other partitions, like something like share positions, that you can attend to multiple tokens from the same positions, or something, we find that this do not hurt the performance. Yeah.
Okay, thank you.
Is there more questions? Yeah.
Oh, just a quick question. So I does I'm not sure whether you use a single GPU or multiple GPU in your inference time.
For current our inference, we use for H100. Yeah. Every experience or efficiency analysis is based on for H100.
Okay, thank you. Yeah.
So I have one more question. So, in the conclusion phase, how did you merge the all the KV cache tokens from different parties? Because if you just directly concat them, however, the conclusion phase should see all previous parties, and the KV cache should be computed. The attention should be computed from like all previous tokens. And however, in the split phase, the tokens are not. For example, path 2 doesn't. The KV cache is not calculated depending on the generation results of part 1. So do you recompute all the token, all the KV caches other than path 1, like from path 2 to all the way into the conclusion path, or you just directly concat the KV caches from different paths for the conclusion phase?
Think about question. I think that first that for our questions, we directly concat them without no more recomputation. And this, I think, is also the reason why we introduce conclusion stage instead of directly let the model to go to the next step. Just we also concerning about that because that the KV cache are from different paths during generation that they may diverge. But actually, that in our previous work, that one paper called Adaptive Parallel Encoding, we already illustrate that if you have a same prefix, that the distribution of the KV cache from different passes is very similar, so that they are something can be combined. This is the reason why we direct combine it. And we introduce this conclusion stage as just we wanted to generate some tokens that just to further align this distribution between the different passes. This is the reason that why we have this stage. So we directly concatenate, and we want the conclusion stage to enable a more seamless merge of different passes. Yeah.
Thank you.
Yeah, it seems that we don't have further questions. Thanks, Xinyu, again for the amazing talk.
Yeah. Thank you. Yeah. Thank you. It seems I invite myself. Yeah. Thank you for hosting me. Yeah. And if you have more questions about Multiverse, feel free to directly email or ask me. Yeah.